In this video, I'm going to be talking about an introduction to bending. And to start off with, there is 3 things you need to know to not embarrass me in engineering studies. The first thing is, by the end of the course, you need to know that concrete equals cement plus aggregates. The second thing you need to know is that stress equals force over area. The third thing you need to know is an example of stress is steel, and steel has a yield stress greater than 300 megapascals. Megapascals is the unit of measurement for stress. Now the thing is, that's not entirely true, right? Dun dun dun. We've learned that stress equals force over area, but that's not always true. That's only true most of the time. There's a time when it's not true, and that's for bending. Bending equals, and that's what we're going to learn today, bending stress, lowercase sigma b, equals my over I. Now, there's 4 things we need to learn about. The first thing is bending stress. So bending stress or bending strength, right, is measured in megapascals. Well, it's actually measured in pascals, but we're going to use always what are called the grease units, megapascals. We learned about grease units yet? Okay. I'll put a video in a second. But the short version is, we go together like megapascals and millimeters squared. You can see it the other way too, but I think that sounds wrong. The idea is that although we're supposed to use base SI units all the time, and that's what Copeland does, very few working engineers will do that. Instead, what they'll mostly do is they'll use megapascals and millimeters. And if you use megapascals and millimeters, everything just works. It just happens to work, right? So that's the thing we need to know. Okay, so we've got bending stress equals that. Now the next thing we have is M stands for bending moment. Now, I don't teach this until you've learned, until we've at least started trusses. So at this point, you should know that in order to find reactions, we find turning moments, bending moments. Now the thing is that when something is being bent, there's a moment involved, and it's equal to its force times distance. So in a very simple beam, we can use the example of just the force times distance. So we know that the force on both sides is going to equal 0, right? The sum of the moments is going to equal 0. But if I have 100 newtons down, what are my 2 reactions going to be?
50-50.
50-50, excellent, okay. And let's say, just to make things easy, I say that my beam is 2 meters long. So this is 1 meter and 1 meter, yeah? The bending moment on this side is 50 times 1, or 50 Newton meters, going clockwise. On the opposite side, we have 50 Newton meters going anti-clockwise. Those 2 forces, when they add together, they balance out to equal 0. Yeah? So when we say the sum of the moments equals 0, that's true. If you measured some of the moments about this point here, let's call that x. If you took some of the moments about point x, it would equal 0. Let's have a look. We'd have 0 equals 50 times 1, or brackets 1 is what I normally would do. Going clockwise, so it's negative. And then we have here 50 minus 50 brackets 1 equals 0. Now, to say that the sum of the moments about x equals 0 and leave it at that, that's pretty misleading. And what I mean by that when I say it's misleading is that if we have a tug of war, right? In a tug of war, if I have 2 kids in year 5, right, and they're doing a tug of war, or I have 2 teams of army men, right, and they're doing a tug of war, there's 5 people on each side, and they're each 100 kilos, and they're just full of muscle. Well, say the rope's not moving. In both cases, the rope is in equilibrium. Yeah, the rope's not moving. Those 2 forces are balanced each other. The kindergartners and the army dudes, in both cases, the sum of the forces equals 0. What you complaining about? But if you're the rope, which one would you rather be if you're a rope?
Kindergarten.
The kindergartners, right? They're going to be putting a lot less strain or a lot less stress on you, right? You'd much rather be the one there's internal stress is very high. Even though the sum of the forces is equal, the internal forces or the internal stresses could be very different. So in this case, what we're trying to find is the internal forces in a beam. If I say, well, I have a beam and I have a piece of wood between two chairs and I sit on it, well, I say, okay, well, it didn't move, right? What's the difference? Or if I then get an elephant to sit on that same beam, well, now the beam's saying, wait. I know that the expectation is that I should be able to balance the forces, but I might not be strong enough to balance the forces. So what we want to do here is we want to determine whether or not the material has enough strength to manage the bending forces. Now, what I'm going to tell you is the quick way for a simple beam like this, right? If I have a simple beam like this, and what I'm going to use, instead of using 100, I'm going to use the letter F or P. A lot of the time we use P, but in this case I'm going to use F. F. And if I said this is L, the distance from one side to the other side is L. But I don't want to use L, I want to use half an L and half an L. Does that make sense? Yeah?
Oh yeah.
Okay, and what's the reaction going to be on each side?
50, I think.
Yeah, 50 side. So what's a way of saying 50% of F? Another way of writing 50% of F.
Half of it.
Sorry?
Half.
Yeah, or F on 2. Is that a way of writing half F? Yeah? Okay, so in that case, in some cases, we can say that M, the maximum bending moment equals F on 2 times L on 2. Now, we could simplify that and we can just write FL on 4. Now, I want to point out that the internal bending moment is going to be lower at Y. This point here, the internal bending moment is going to be lower than the bending moment at X. Does that make sense?
Because it's like closer to the thing.
Yeah, it's closer to the edge, right? So the closer, if I was to draw this in a diagram, it would actually look like this. The maximum bending moment would be here. Now we said before when it was 100, it was 50 times 1. So we said it was 50 newton meters, right? So that was 50 newton meters. Here, it would only be like 25. But if we want to test our rope or our beam that the elephant's going to stand on, right? In any of those sorts of situations, well, we want to use the maximum. We want to know if it's going to break, right? We're going to know. We don't care about the hypothetical. Now, this diagram looks very different depending on different load conditions. But for the moment, we just want to use a simple diagram, right? And so for the simple diagrams, right, for a simple single symmetrical load, we can use this rule, the M equals FL on 4. Okay, the next thing we want to do is we want to find Y, right? Now there's a Nora Jones song called Y, and then there's a Sesame Street version of that, but we don't have time for that. So instead, what we're going to look at is we're going to take this beam here, right? And I'm going to bend this beam. I'm going to bend it in the middle downwards. So when it bends, it's going to look something like this. We good with that? Now, a way that I've been told to explain this when I did tutoring, right? A student said to me, hey, you should explain it like this. I don't know if she came up with it or if a teacher mentioned it, but one way or another. These two circles at the top, are they closer or further apart?
Closer.
Closer, so they're being squashed. So that means they're in what? In tension or compression?
Tension and compression.
Compression, because they're being squashed. The ones on the bottom, they're being stretched, so they're in tension. And if you actually take a piece of timber and you bend it enough, you'll actually start to see it split split apart where it will crunch at the top and stretch and get cracks on the bottom. Concrete usually fails on the bottom, right? That's how we design it. We under-reinforce it in the tension side. Okay, now here's the thing. At this point, this piece of, let's say timber, right, for the sake of timber, that grain of timber, that element of timber, right, that molecule of timber is probably a better term, it has as much compression as it's possible to be. Well, actually no. This is as much compression as it's possible, because we said that the maximum bending is in the middle, right? But this part here is being squashed more than that part, so because we said in the center is where the maximum bending is. But what I want to look at here is I want to look at down the beam. This part here, is it being squashed as much as the part above? Is it equal squashing or less squashing? Less squashing, that's interesting. Okay, well, what about here? This part here is in maximum tension. It's as much tension as it's possible to be. But somehow here, it gets to being zero tension. Yeah? Because somewhere it does a swap. It doesn't go like this. Compression, 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 swap, tension, tension, tension. It doesn't do that. What it actually does is that the top bit of timber is under the maximum compression. This top part of the timber is under maximum compression. And this bottom part is under maximum tension. And then somewhere in the middle is what we call the neutral axis. Right? So I always like to think of it's like the Grand Old Duke of York. I don't know if you heard that song as kids. The Grand Old Duke of York, he had 10,000 men. He marched them up to the top of the hill and he marched them down again. And when they were up, they were up. And when they were down, they were down. And when they were only halfway up, they were neither up nor down. Maybe you thought that was a waste of 10 seconds of your YouTube life, and you'd probably be right to think that. Anyway, in this case here, what we're saying is this part here, this entire line, there's no stress. No stress from bending anyway. At this line, it's not compressed. It's not in tension. It's just there. So this part here, it's under zero stress in this axis. There's no stress there at all. It means you can actually, if you want, you can actually drill holes in here without really affecting the bending strength. You might affect other strengths. You might affect the compression. You might affect other things. But tension's probably the bigger concern actually. Assuming you're going to fill in the hole. So what we find is that it's interesting that in this beam, this is the maximum bending, this has less bending, and this has less bending again. Yeah, because we know bending is at the maximum in here, right? Bending is the maximum in here, and we know that the stress is a lot bigger on the outside layer, right? The layer next to the paint is under a lot more load, right? Under a lot more stress than the middle. The middle is doing nothing; it's just sitting there, right? And what that means is that we've talked before about how if I have a metal ruler, and one day I'll do this, recording with an actual metal ruler in my hand. If I have a metal ruler and I have it standing up, it's a lot stronger if I'm trying to bend it than if it's flat. If it's flat, I can bend it pretty easily, right? I can, I'm sure that you must have known a kid in your time at school who has bent a metal ruler, right? Whereas if you have it standing straight, it doesn't bend very easily because the distance from this neutral axis is much bigger if it's standing up. If it's standing up, the distance from the neutral axis is bigger. And the bigger the depth of your beam, so if this is my beam looking sideways, right? That's looking in this section. I'm looking I'm imagining looking at a cross-sectional area. If it was timber, it would probably look like that, right? With the grains of the timber. Yeah? If I'm looking at that, we call this the breadth and we call this the depth. And the bigger the depth, we've talked before about how if we have two beams, I could buy a beam that's 100 by 100, or I could buy a beam that's 50 by 200. Well, this one's much better for columns, and this one's much better for beams. Yeah, and this is why roof beams, right, which we call rafters, or floor beams, which we call bearers or joists, this is why they tend to be taller rather than equal sizes. Now, if you take, so for instance, a floor joist is usually 50 by 100, right? And then a bearer is usually a little bit wider, 75 by 100. But what I've done is I've just added an extra 50% of the wood. If I instead had gone this way, 150 by 50, that one would be better for bending. Yeah, that would be better for bending. There are reasons why you might not want to do that, right? Generally, if we're buying steel, what we often do, if we're buying like really high strength steel, is we buy what we call universal beams, which look like this, or universal columns. And the reason why is because we know that the more steel there is at a long way away, they're going to be dealing, we want more steel to deal with this high area of compression and this high area of tension. We don't need as much for this area where it isn't doing as much. For columns, it's a little bit different. Columns, we have to assume they're bending in both directions, right? A bit different for columns. Okay. Another term, if you use older universal beams, also called I-beams, they're rolled steel joists. You don't see them as much, but sometimes you might see, like, I always talk about how in faulty towers, that's where I remember them saying rolled steel joists. Or in Futurama, Bender, he bends girders, right? Girders are really big beams, right? They're ones that have been welded in place. After 600 mil, you can't buy them anymore. You have to make them yourself. After 600 mil, that's the biggest beam you can get. So things like monorails, they have to be welded girders, and that's what Bender bends. Okay, so all of that is to talk about what is this Y, right? Now at uni, they call it YBar, and YBar is the distance from the neutral axis to the extreme fiber. Like fiber, when you eat fiber, it helps you to be more regular in the toilet. So I like the idea of, if you really need to go to the bathroom, then you need extreme fiber. Anyway, so when we say the extreme fiber, we mean this bit of timber here is the extreme fiber. It's as far away from the neutral axis as you can get. What is the distance from this line to the extreme fiber? Now the fact is, why not just say half the depth? Because isn't it always going to be half the depth? Yeah, do you see how it's half the depth? Yeah? But the reason why we have to say that is because sometimes we don't use a symmetrical beam. Sometimes we use T-shaped beams. Now, I have personally always hated T-shaped beams. Maybe there's an engineer out there who didn't hate T-shaped beams, but I don't like T-shaped beams. When we have a T-shaped beam, what we get there is, well, we still have our bending. It's worse than the last one. Okay, but here we'll find that the neutral axis is much closer to the top. The neutral axis will be up here. And that makes sense because there's just so much stuff up the top, right? There's so much mass up the top that the neutral axis is going to be closer to the top. Okay, and so how that looks is here, it looks something like that. The neutral axis okay, took me quite a few attempts to get that. In this case, the diagram looks something like this. You have stacks of compression up the top, but see how the area in the compression zone has to be equal to the area of the tension zone? Yeah? So do you see how in this situation, the area is about equal, but a very different shape. Yeah, so in this case here, the distance from the YC is very different to the YT. Yep. So in this case, YC is not always equal, so YC is often equal to YT, which is often equal to D on 2, but not always. Okay, what unit would we use to measure that? What unit would we use to measure the Y? No, it's a distance, right? Millimeters. Millimeters is the answer. Okay, the last thing we're going to find is we're going to be given the I value, right? I, and I'll write this one over here. Right now, space. I equals, well, I like to call it the moment of inertia. And I like that name because it starts with an I. Yeah, moment of inertia. Yeah, it kind of helps you to know what's going on. The thing is, most people don't call it that. Instead, they call it the second moment of area. Okay, so here's how you do it. What you do is you find your area. Like this, right? You say, what's your area? And then you say, okay, so let's say we take a measure from the top, right? You say, what's the area? And we'll say, well, the area is 100. And this one here is 100. And this area here is 100. And then what I want you to do is I want you to take the moment of area, so it's going to be 50 times 10, say. So 100 times 10. And this one here is going to be 100 times 50. And this one's going to be 100 times, I don't know, we'll call it 130. Yeah, we're measuring the distance and we're multiplying it by a distance. So we're taking a moment is a force times a distance, and so this isn't a moment that's a force times a distance, this is a area times a distance. And if you're having an area times a distance, it's going to be in millimeters cubed, right? Because you're taking an area and then you're multiplying it by a distance. Yeah? What you're trying to do is you're trying to figure out how much area is there and how far away is the area. Then the next thing you're going to do is you're going to take the second moment of area. You took that first moment of area, now I want you to take it from again. And when you multiply it by a distance again, now you're going to get moments to the power of 4. That's why they call it a second moment of area. And it's measured in the most ridiculous unit of all. It's measured in meters to the power of 4, or we will use instead millimeters to the power of 4. Now, in the HSC, this will be given to you. Right? It says in the syllabus, right, you have to do calculations with the second moment of area provided. But it is possible to calculate the second moment of area. You do this at uni, you probably do the second year uni. Okay. So I will sometimes do calculations or equations where it's BD 3 on 12, right? That's for a rectangle. Obviously it's different for a circle, it's different for an I-beam. For an I-beam, much more difficult, right? And if you buy a piece of steel, they will give you a document that will tell you the second moment of area in the document. Right? You can look it up on the internet. If you say, what is the second moment of area of a UB610, they'll tell you what that is. Okay, so let's just pick a simple question and I will figure out the I value for you. I'm going to give you a... Okay, I'm going to use a very simple rule. Let's say that I want to take out this whiteboard. I'm going to remove the whiteboard, but I need to replace the whiteboard, the area of the wall. I want to make a big hole in the wall, right? And this distance of the whiteboard, I need to replace a beam to hold up the roof, right? Because presumably some amount of the roof is on that whiteboard, yeah? Not always. Sometimes you might live in an apartment, and in an apartment often walls aren't supporting any load. They're all being held off the like the central like sort of elevator shaft and a couple of columns maybe here and there. Everything else is just cantilevered. But let's assume that this wall is supporting load. And what I'm going to do is I'm going to replace this. Well, what I would do is I would measure how many feet is the whiteboard, right? This is a rule that doesn't really work anymore, but we'll talk about it. So it's 1 foot, 2 foot, 3 foot, 4 foot, 5 foot, 6 foot, 7 foot. 7 foot whiteboard? Well, that would be 8. I'm going to call it 8 for the sake of argument, right? So the rule that builders used to use is they'd say half the feet in inches. So 8 foot, right? 8 foot divided by 2 is 4 foot. And so you'd have 4 foot, 4 inches, right? 4 inches, pretty standard beam, right? 2b4, you hear people talk about that. Even in a board game we've got that they're talking about 2b4. A 2b4 is the same as a joist, 50 by 100. Now the thing is, you have to use good quality wood to do that, right? That's the problem with this rule, is you have to use hardwood. So for us, we might say, well, we don't have hardwood, so instead we're going to use, we're going to double the beam. That's what we're going to do. We're going to go double because our wood's only half as strong. So we're going to go instead 200 by 50. 200 by 50, I will calculate for you the I-beam. That's what we need. 50 times. Okay, so the answer I get is 3. 33, and then 3, 3, 3, 3, 3, 3, right? But millimeters to the power of 4. But instead of doing that, what I'm going to do, you see how it's millimeters because it's that times that times that times that. Anyway, you get the idea. But instead of writing that, I'm going to replace those zeros, and I'm going to say instead times 10, well, let's say 33.3 times 10 to the 6 millimeters. So the 10 to the 6 means that it's a million millimeters. And that's really convenient for us, right? We like that it's that because Copeland, he will instead write it as a really small number, and he'll do it all in meters. Too hard for me, right? You can follow that method if that works for you, but this is the way that every professional engineer I know would use. Okay, so I've given us that value. Now the thing is, I've then said, well, the distance between our beam was 8 foot, which is 2.4 meters. That's what our L is. What's the F? How much load is there from the roof on this thing? Well, probably is a minimum. Oh God, it's a big room. 5 times 10, 50 kilonewtons, right? Just pick the number. 50 kilonewtons probably work. Okay, so that's our F. So that's a very simple version of what's going on, right? It's a very simple version of what's going on. Now, what then, if we use that formula, what would our M be using this formula over here? M max, our maximum bending moment, is going to equal what?
FL.
Yeah. So FL on 4. Just to prove that, what it would look like is it would be that distance, 1.2 meters times 25 kilonewtons. So that should be the same thing, right? Let's see the answer we get. We get 50 times 2.4 divided by 4. Now remember, we can only use this in very simple situations. 2.4 divided by 4 equals 30 kilonewton meters. Right, remember it's in kilonewtons multiplied by meters, so it's kilonewton meters. 1.2 times 25 equals 30. Yep, okay, good. Okay. What's our I value? Well, I said our beam was how big? I said it was 200 times 50. Yeah? So what's our Y value? Are we okay with that? Yeah? Because our neutral axis will be in the middle. Yeah, so our Y value will be half. Okay, so what's our bending moment? Our bending stress is going to equal M, which we said was 30. Okay, but it was 30 what? It was 30 kilonewton meters. We said instead we go together like megapascals and millimeters squared. Well, I didn't mention newtons at all in that. So that means we have to use regular newtons. So that means we have to use 30,000 Newton meters. Okay, how many millimeters are there in a meter? Millimeters in a meter. If you have a meter ruler, how many millimeters are there? 1,000. So that means there's 30,000 Newton millimeters. Another way of writing that is we could write 300,000. Okay. 30 times 10 to the 6 Newton millimeters. Yeah? Okay, so we've now got all the information we need, right? We're going to write sigma b equals m times y divided by I. Let's have a look at that. We've got 30 times 10 to the 6 times I, what's I? 100 divided by 33 times 10 to the 6. Yeah? Okay, so what's our answer going to look like? Well, it's going to be about 100, right?
Yeah.
Yeah. So,
Would the 10 to the 6's cancel out?
they will.
So it'll
And the
just be
30s are going to be
100
pretty close
divided
together
by
as well.
10.
So the answer is going to be about 100. Yeah, a little bit less than 100. Oh, yeah, times 100. .09 megapascals. Okay, now I'm concerned about that because that's a far away. Okay, what did we say steel can hold?
More than 300?
More than 300, right? So for steel, you're like, oh man, the steel can hold this easy, right? But for timber, that's too much. Timber can hold about 5, 10, something like that, right? Hardwood can maybe hold 10, so it's still way too much for a timber beam to hold. Which means my rule, I don't know, maybe I did something wrong, maybe I added too much load. Anyway, but that is the answer we're going with here, right? That's the answer. What I'm going to do now is, so steel, easy. Steel's got a factor of safety of how many? If we said steel can hold 300, what's its factor of safety?
200?
Well, it's got more than 3 as a factor of safety. The factor of safety is more than 3 times what we're allowed. Yeah. Okay, so in this case here, it would no good, right? Steel, factor of safety of 3. It's a big piece of steel though. Okay, so that will do for this lesson. I'll do another example.